Test, test. All right, everybody, we're going to go ahead and get started for the evening. My name is Tyler Staggy, the former mechanical lead for the Purdue IEEE ROV team. I will be leading the session tonight. We have Logan Walters, another former mechanical lead for ROV, hanging out in the Discord. He'll be answering you guys' questions if you have any. Feel free to drop them in the general channel there. Or if necessary, Logan can hop into a breakout room with you guys. I will be keeping an eye on the Discord, but there is a bit of a delay between the stream and the Discord, about 30 seconds. So I think with that said, we're going to go ahead and get started. This is session 3. It's a bit of a mishmash. We're going to be covering drawings, as well as some other more advanced modeling techniques, things you guys should be aware of. The slides for this session are available at that tiny URL right there. That link is also in the YouTube description, and you can find both the slides and some of the exercises we'll be doing have some files you'll need, and you can find those there. So this is the third session. This is the last one. This is the virtual session. No need to. All right. Yeah, so like I said, the content will be drawings, and then some of the other techniques we'll be going into are equations and global variables, surface modeling, and skeletonization and other interpart references. This is our map of the product lifecycle management, and so we're dabbling into drawings and documentation, but still have a foot in design here today. All right. So the purpose of drawings, engineering drawings, they're technical documents that contain basically all the information needed to manufacture any given part to your required specifications. It includes materials, obviously dimensions, and the required manufacturing tolerances, and sometimes some additional information. In industry, there'll be quite a lot of standards you'll need to follow. Those standards exist because drawings are a primary means of technical communication, and for all you know, as students, we generally make the parts we design. But once you're in industry, for all you know, the supplier that's actually making your part could be halfway around the world, and very clearly made and complete drawings are necessary to avoid a lot of confusion, delays, and potentially costly mistakes. This is not a particularly good drawing, but this is a good sort of overview of what the main sort of content of an engineering drawing are. You have your sort of standard view layout. It's not exclusively always three specific views. It's as many views as is necessary to communicate all the information, but sort of 3 views is sort of a typical what you might expect. You generally also have an isometric view, sort of from an angle there. That is generally undimensioned, just to help the reader get a better sense for this part in 3 dimensions. Then you have your title block. Includes part number, author, company, any sign-offs that have to be done. So who checked the drawing, who approved it. That can have legal consequences too. In SOLIDWORKS, when you actually go to create a drawing, it is a separate file type. We have .sld.prt for parts, .sld.asm for assemblies, and .sld.drw for drawings. Just like assemblies, they reference other files. So it's another case where good file management is necessary, because if you rename a part that a drawing is referencing, you break the link and you'll have to relink it, and that can cause issues. Some of I referenced standards. The 2 major ones to be aware of are ANSI, the American National Standards Institute, and ISO, the International Standards Organization. That's effectively metric. The metric standards. There is also a third organization, DIN, D-I-N, that is the German standards organization that is generally aligned pretty closely with ISO. I'm going to open up a drawing here in a second to guys sort of show you the process. In addition to the distinction between U.S. units with ANSI and metric units with ISO, one of the other differences is the actual sort of standard, what's called the angle of projection, that is used. And this is kind of hard to explain over audio, but this graphic here represents sort of the distinction between first angle projection and third angle projection. It's basically how the top, left, right, and side views are sort of arranged next to each other on a drawing. With first angle projection, you can sort of imagine it as the part rotating on top of the page, 90 degrees in each direction. And with third angle, you can kind of imagine as the part rotating 90 degrees, but sort of behind the page. And these are the sort of the standard symbols that are used on drawings to indicate which type of projection you're looking at. Before I go any further, I'm just going to go ahead and open up a drawing in SOLIDWORKS. So we're going to go up to New, Drawing. You have your choice between sort of the standard ANSI and ISO sizes. I'm just sort of going to arbitrarily pick this first one here. You can also do custom sheet sizes. I tend to use that a lot to get actual 8.5 by 11 drawings that can be printed on a standard printer paper. Just like with an assembly, when you create a new drawing, it will prompt you to insert your first part. You generally only ever insert one part, but technically you can add views for multiple. So I'm just going to take this demo part here. You can see it's sort of prompting me to place my first view, and it's actually, you can select which is sort of the base view that you're placing. We'll just leave it as, what is that, front? Yeah, front. Let's go ahead and place that front view. And then as you place your cursor to any given side of the sort of the first view that you place, it'll give you the option to sort of add additional projected views as desired. We'll just do a quick 3 view with an isometric. And then I'm just going to hit OK. You can see as you move these around, they're linked together. Isometric is a bit unique. It doesn't move with the rest. All right. So a few basic things. Changing the scale. If you select the sort of the base drawing here, you can see it's set to use the sheet scale, sort of the global variable there. You can also set it to use a custom scale, say 1:1. That would change that. But if you want to use the sheet scale, the way to change that is up here. So if you have sheet 1 and you have sheet format 1. So I'm going to right click on that, go to properties. This is where you can This is where you can edit the name. You can change the global scale. You can change the sheet size. That'll readjust everything. You can also change the type of projection between first and third if you'd like. For now, I'm going to go with a slightly less than standard 2/3 scale, just to make everything fit nicely. All right, let's say we're happy with that. You can see it's sort of like default populates a bit of a title block here. You can edit that by right-clicking again on sheet format and going to edit sheet formats. This gives you a view of sort of your border and title block and anything else there that you can edit. And you can do things, I believe, yeah. So we can say, part name right there in title. Let's say we want to call that just part number. You can add if you're the author, you can add that, add your name there. You can also edit these. It sort of acts like sort of sketch geometry, or if you'd like to sort of get rid of some of this content, you can do that and then sort of drag these lines over. And in general, odds are if you're working within sort of a student organization, you'll probably have a sort of a default sort of template that you'll use for all drawings. ROV, for example, has one that I worked up just to avoid the headache of editing all that every time. To just get you the information you need without taking up more space than is necessary. All right, so this is our basic view. By the way, you can also change sort of the view type in here. Almost all drawings are sort of monochromatic like this. If you wanted to, for some reason, you could add in shaded views. You could also, if you want to see hidden lines, you can turn that on there. For now, I'm just going to leave it like that. And then adding dimensions is actually fairly similar to adding dimensions in sketches. We have the annotation tab up here, and we have the Smart Dimension tool. I've got that linked to a keyboard shortcut D. And you can come in and select any edges you want. And I believe this part was designed in inches, and this is currently in millimeters. So I'm going to switch units. I'm going to go down here to this bottom right-hand corner, go to Edit Document Units. I'm going to go to inch, pound, second, and here is also where you can change the number of digits displayed. If you're just doing something for yourself, say a reference, so you're going into the ME machine shop and you're going to make a part, then you might want to give yourself 4 digits, just because that is the number of digits displayed on the mill's digital readouts, for example. But anyhow, yeah. So you can select lines, you can select between lines. You can also, by default, most holes will get these center marks auto-populated, so you can reference those to place dimension to the center of the hole. If those do not populate for some reason, or you accidentally delete one or what have you, those can be achieved up here still in the annotation ribbon up here, center mark. I'm going to show you real quickly how to insert a cross-section view, because you aren't limited to just projected views. You can also do detail views, where it's just like you zoom in, you draw a circle, and it'll give you a blown-up version of just that detail. Or another common one is a section view. So you go up to under drawing, go to section view. You can sort of just hover over one of the views, and you can switch between horizontal, vertical, or if you want more of a complicated section, you can actually draw a series of lines. And it'll create a section that follows that. For now, I'm just going to do a quick vertical section right there. hit the checkbox, and that'll just let me project it over there. And this is standard. Sections are labeled with capital letters. If you'd like to, you can actually change those here. For example, I could change that to B, and then the view here is labeled section BB. Some other important things, like I said, I showed you center marks. You can also add center lines for any sort of cylindrical surface that is like perpendicular to the view you're looking at. So in this case, that is just a hole right there, a tapped, I believe, M16 hole, and you can add a center line there if you wanted to dimension the position of that hole on this view here. You wouldn't necessarily do that though. What are some other important things to note? If you just want a sort of a general note, you can also add that there. That basically just creates a text box. You can also add notes to existing dimensions. You can sort of edit the content of the text of that dimension there by if you just select it, and over here in the dialog box you've got dimension text. That is sort of like, theoretically, if you wanted to, you could actually just completely overwrite the dimension. But if you didn't want to do that, say you wanted to label that as, I don't know, something like, if I can type, width. Yeah. Generally, if it's some dimension where you want to label it just to keep things clear. I think that is sort of the basics of starting up a drawing. With that, I'm going to head back to the slides. Actually, yeah. So the next topic is sort of adding tolerances. Obviously, so in CAD, the geometry you create is the ideal geometry for that part. All of the dimensions that you include in your model are the nominal dimensions. But any actual manufacturing process obviously is going to have error, and drawings give you an opportunity to specify how much error is allowable, where your part will still perform the job necessary. And you can do that just by, actually, let me go back to SOLIDWORKS real quick. You can basically just select a drawing or select a dimension, and then if you get this pop-up sort of dialog, I don't know what you exactly call it, but you get this pop-up that you can open up, and you can edit tolerances here, or you can just select it and then head over here to tolerance and precision, and you can add, say, symmetric tolerance, or say we want that to be the placement accurate within plus or minus 10 thousandths of an inch. You can do that there. You can also add asymmetric. I believe those are bilateral. Yeah, so if something is allowed to get bigger but not smaller, you can do that there. And you have a number of different options there for how to specify tolerances. One thing to keep in mind when adding tolerances is stack-ups. So this is sort of a function of what actual dimensions are you adding the tolerances to. If you just have a really simple part here, just sort of a brick with two holes in it, you can add dimensions between all these objects here, so between the edge and the holes. And if you say 20 millimeters plus or minus 1 millimeter, if you add that up across the whole length, it means sort of the width of your part here can be anywhere between 57 and 63 millimeters. Where if you dimension it more like this, your length will be anywhere between 59 and 61 millimeters. So it's important to keep in mind how all of your tolerances interact with each other. And to sort of clear up some of the, to more precisely express what is the tolerances that are necessary for your parts to work, there is a system called GD&T, Geometric Dimensioning and Tolerancing. This is definitely beyond the scope of this training, both because we don't have the time and because none of us actually, at least I don't have the expertise to really talk knowledgeably about this. But just be aware that if you're in industry, odds are you'll be using GD&T. So it's definitely a good thing to become familiarized with. If you happen to be in mechanical engineering, the machine design textbook, Shigley's Mechanical Engineering Design, I know has a great chapter on GD&T, and there's also plenty of other information available online. But effectively, it's just a standardized system of symbols that is designed to very compactly and very precisely communicate tolerances in a more geometric fashion than strictly just adding plus or minus values. And SOLIDWORKS and any decent CAD package also has the ability to add those. These are called control frames. You can see there are a bunch of specified symbols. And that is up there on the annotations tab, all the tools you need to add GD&T tolerancing. Yeah. Of course, as a student organization, odds are when you're making drawings, you don't have to conform to those standards necessarily. You're generally creating drawings as references for yourself. So here is an example of a part that I was making in the ME machine shop. So all the information on here is tuned to exactly what I needed. So in this case, it was a solenoid manifold. And when you're using a manual mill or any mill, you probe your part to define an origin. In this case, I had probed the part in the mill to set this top left corner as my origin. So basically all of my dimensions are referencing that top left corner. So I basically limited the dimensions that I put on here to the actual numbers I would see on the digital readout as I was moving the tool around the work. And if you'd like to, you can even, there is a sketch tab within the drawings where you can add extra geometry to tolerance off of here. I drew in some extra circles, basically represented the diameter of the tool I was going to use, and sort of dimensioned to the center of that to tell me what's the center of the tool in order to achieve this geometry. You can also do things like, you can also, when it's just a reference for yourself, you can also do things that would definitely not be allowable on a proper manufacturing drawing, like add in, if you're not exactly sure what drills the shop has available, you can add in like the ideal size and the closest sizes that would still suit your purposes. Those sorts of things. Excuse me. All right. Very sort of basic overview and intro to drawings out of the way. We're going to move into some of the quote-unquote more advanced modeling techniques that we alluded to. And we're going to circle back to drawings at the very end if we have time, just to do some more exercises to show you guys a few more things. All right. For now, equations. This is one of the really powerful things about engineering CAD. It's definitely something that is good to be aware of. So when you're just in a sketch, you can use equations to set some dimension to some function of another dimension within that sketch. So, and it's when you create a dimension here within the dimension dialog box, if you were to type equals and then click on some other dimension in the sketch, it'll auto-populate that name there, and then you can say, in this case, like, times 2. So I want the length of this edge on this part to be twice the length of this edge. And when you do that, SOLIDWORKS will add in this red sigma to indicate that this dimension is driven by an equation. And when you do that, if you were to update this dimension, as you can see here, it'll auto-update this other dimension. And that can be really handy. Sometimes, though, if you just want two dimensions to be equal, you can also, in a bit more compact way, you can also just use the equal constraint. So you select that edge and make them equal. That can be handy for reducing clutter on the screen. And you can even, it's one of the useful instances where construction geometry comes in handy. We can create two construction lines and just set them equal, and that achieves the same thing as two dimensions would. But let's say you want some parameter, some feature. Like if you were to extrude this part and you want the actual sort of width or height you extrude it to be a function of some variable that is also used in a sketch. The way you do that is with a global variable. And I'm going to show you this here in just a minute. If you go up to Tools and then to Equations, you get this equation editor here. And that's where you can do things like create global variables. So in this case, created a global variable called stock thickness. Set that to 6 millimeters. And now that is just a variable that we can reference both within sketches, if you wanted to, or within sort of the dialog boxes where you're defining features. In this case, an extrude feature. You can reference a global variable in either of those cases. And a good example of when something like this would come in handy are threads. So these slides may be a bit out of order compared to the PDF that you guys have, but if you sort of go down to the end of near the end of the PDF, there's this exercise. So what we're going to go ahead and do is I'm going to pop over to SolidWorks, and I believe, yeah. So this is the zip folder that's up in the tiny URL should give you these 4 folders. So I'm going to go here into exercise 1, open up the part, and as provided, it should look something like this. So let's say we want to model a thread. Let's say this may be like a custom shoulder bolt or drawbar, some part you're designing that where you want a thread on it, and you actually want to model that. So as provided, I believe I have a sketch here called thread form where I've sort of worked out the basic geometry, and you can see here. So this here is a ISO standard thread form, a metric thread form, where basically all the dimensions here are functions of one variable labeled P here, and that is the pitch. So in this case, what we're actually going to be making here is what's called an M10 by 1.5 thread. M10 means it is a metric thread with a 10 millimeter major diameter, so sort of the top of the teeth of the thread. That diameter is 10 millimeters. And by 1.5 means it has a pitch of 1.5 millimeters. It's effectively the spacing between the threads. So back to SolidWorks. So what I'm going to do, you can see I've got the basic construction geometry here that has all the constraints. I've already dimensioned this to be 60 degrees. Most threads for just fasteners are 60-degree V threads, they're called. And what I'm going to do is I'm going to go up to Tools, and then Equations. And that'll open up our equation editor here. What I'm going to do, I'm going to create a global variable called pitch, tab over. I'm going to set that to 1.5 millimeters. It is important to include the units here. I'm going to hit OK. And after you've done anything in the equation editor, you'll get this new folder here in your feature tree called Equations. And to get back to the equation editor, you can right-click on that, hit Manage Equations. Anyhow, so we are here in the sketch. If you want to edit it, so you right-click and hit Edit Sketch. What I'm going to do here is I'm going to create a dimension. Select the line here that effectively represents the spacing between the threads. And in this dialog box, I'm going to hit equals. It'll prompt me down here. I'm going to go to navigate through global variables and select a pitch. And you can see now we got that red sigma that indicates that this dimension is driven by an equation. And now we'll also need to make sure that sort of the width here at the top of the tooth is 1/8 the pitch. So I'm going to go Smart Dimension, zoom in here on this construction line. And I'm selecting that to be equals. Navigate down to Global Variables Pitch. Excuse me. /8 divided by 8. And ba-bam. So that is now set to be 1/8 the pitch. Now the last thing here is sort of the bottom of this tooth here has to be 1/4 the pitch wide. Go to Smart Dimension, select this line here. Again, equals global variable pitch, and then divided by 4. And as you can see, now all the geometry here is black. It is fully constrained. You can see, here this is effectively just a drawing labeling all of these dimensions. We don't actually need all of these dimensions in order to fully constrain the system because we've used a bunch of constraints here in the construction geometry that does the same job. Anyhow, so we're going to back out. By the way, when you're exiting a sketch, the X here is exit and do not save any of the changes you just made, and this is exit with saving the changes you just made. So now the next thing we need to do, so the sketch we just made here, thread form, or just edited, I should say, has one closed loop. Most of this is construction geometry, but there's one closed loop here. and we're going to use this to create our threads with a swept cut. But in order to do that, we need to specify the path that we want to sweep this along. And most of the time when you're using a sweep, you generally define the path with another sketch. But you can also use 3D curves up here in the Features tab. You go to Curves, drop down. There's a pre-built option for helixes. So if you hit that option, it'll prompt you to select a face. It's basically sort of the starting plane of your helix. I'm just going to select the end here. And then it'll sort of effectively open up a sketch here. And it doesn't explicitly tell you, but what it wants you to do is to draw a circle that effectively defines the diameter of the helix it's going to create. So what I'm going to do is I'm just going to draw a circle. Then you have a couple different options to actually get it to the right diameter. The diameter also doesn't really matter too much here, but anyhow, if you wanted to, for example, you could select this edge, that circular edge, while holding Control, select this edge, and then say co-radial. If you wanted to, you could also delete that constraint. If you wanted to, you could also select the circle, hold Control, and select one of these vertices here, and hit Make Coincident. Either way, it'll do the same thing. So now if we exit out of this sketch, it now gets us into the rest of the helix tool to define the other parameters we need. So there are a couple different ways you can define the helix. You can do pitch and revolution. So what is the spacing between the, I don't know what you call this, well, for our purposes, it'll be spacing between the threads. And how many revolutions you want it to do. So you can change that to 2. You can also do height and revolution. So I want my helix to be, in this case, like 20 millimeters long and 2 revolutions or 3 revolutions. But what we want here is actually height and pitch, because we want to control the pitch. That's kind of one of the whole points here. And I'm actually, to get this going the other direction, I'm going to check the reverse direction option there. And almost basically every threaded fastener you'll ever encounter, not exclusively, but almost all of them are what are called right-handed threads. It refers sort of to the direction of the helix. So the two options are right-handed and left-handed. For that to make sense, you can just Google the right-hand rule. Essentially, you hold your right hand out and sort of point your thumb in the direction you're going, and then your fingers will curl in the direction that the threads will rotate. And that's tricky to explain over audio, but if you Google right hand rule, that'll should become pretty clear. Anyhow, so I may have mentioned, I don't think I explicitly wrote it out here, but what we are going for is an M10 by 1.5 thread. So that means a 1.5 millimeter pitch. So I'm going to set the pitch here to 1.5 millimeters. And so this is kind of a funky thing with SOLIDWORKS, where there are a number of features, in this case, like defining a helix and spiral counts as one of them, where for some reason it will not let you directly set this equivalent to a global variable. Like if you hit equals, it won't give you an option to select a global variable. And in fact, if you tried to type out an expression for it, I don't believe it would work, but maybe I haven't tried that explicitly. Anyhow. But for now, we're just going to call that 1.5 millimeters. And height here, something between 20 to 20, I believe, somewhere between 20 and 25 millimeters will work. So I'm going to hit that checkbox. So that has created for us a helix that we're going to sweep our thread form along. But to make sure that the pitch of that helix is actually referencing our global variable, I'm going to go back here to the Manage Equations tab, or the equation editor. And then I'm going to change the view here. So this currently is equation view. So this is global variables and every equation we have that we have defined throughout our part. I'm going to change it to, I believe, dimension view. So this is now just every dimension that we've defined in our part. That includes dimensions within sketches here. You can see D2 at sketch 1. That's the second dimension we defined in sketch 1. But also features show up here. So we have a fillet feature here called lathe tool radius. You actually see the dimension, or I believe that is the actual radius. So the radius of that fillet actually shows up here. But yeah, what we want is the helix and spiral that we just defined. You can see here there are 4 parameters here, and the one we want here is the 1.5 millimeters. That was our pitch. So to make sure that this value updates as we update our global variable, we're going to make that an equation. So we're going to set that equal, navigate down to global variables, pitch. And now actually if we go back to the equation view, maybe I have to hit OK first. Pitch, OK, there we go. And now just one more time, I'll open that back up. Now if we go back to the equation view, we can see we have our global variable and then all 4 equations we have defined throughout our part that reference it. Cool. I'm going to hit OK. Now to create the sweep we want, I am going to select the helix, hit Control, select the thread form, and we're going to go up under the features ribbon. We're going to go up to swept cut. You can see there it is sort of taking the closed contour from our sketch and then sweeping that along the path we've just defined with our helix. And we don't actually have to make any edits here. We can just hit OK. And then to hide the helix now that we've used it, we can just click on it and hit hide. So cool. We now have a fully formed M10 by 1.5 thread. And now the reason we went through all the shenanigans with the global variable is so, like, you know, there are multiple different sort of standard pitches for a lot of different size threads. So I believe, so M10 can come in 1.5 millimeter pitch, or a less common is a 1 millimeter pitch. So if we wanted to switch between sort of the coarser thread here, the 1.5 millimeter, to a finer thread like 1 millimeter, if we hadn't defined a global variable, we'd have to, you know, edit those 3 dimensions in the sketch and then also edit the pitch in the helix. But since we've defined the global variable, we actually just have one value we need to change. So I'm going to go up here, manage equations, and I'm going to set this to 1 millimeter. And so that change will propagate down to all of the equations we have defined. And ba-bam. You can see there that if we open back up our thread form, you can see that these values have changed. This was 1.5, it is now 1. And as you can see, it also got finer. So our helix, right there, the pitch also changed. So it's now one-stop shopping. We just have to change one value to update the threads. And that is this is sort of a simple example, but you can definitely have more complicated parts where you have a lot more references to the same value. So that in cases like that, you get a lot of benefit from defining global variables. You can save a lot of time. While we're here, before we move on to a somewhat unrelated topic, I'm going to show you a few more miscellaneous things that I do not believe we have gotten to in previous sessions. And that here is going to be defining materials and changing appearances. So defining materials is an important part of documentation. Materials will show up on your engineering drawings when you create them. And within CAD, if you define a material, it can also be used for estimating the mass of your part, or when you get into more advanced stuff, if you actually do finite element analysis, FEA, basically sort of stress simulations, you can do simulations for more than just stress. You can do heat flow, stress, etc. Yeah, you'll need to know the material properties of your part. And the way we do that, the way we define what material this is we go up here. It shows up in your feature tree, material right here. And by default, it is not specified. But if you right click on that, hit edit material, SOLIDWORKS has a preloaded database of a bunch of different materials. So for example, if you navigate down, you can see it's got a bunch of different steel options. It's got a bunch of different aluminum alloys. If you go to plastics, there are a bunch of different plastics, you know, ABS, acrylic, what have you. In this case, we're just going to somewhat arbitrarily choose a steel. I'm going to call plain carbon steel. You can see here, it's not just the names of the materials, but it's actually got important material properties. Elastic modulus, which describes the stiffness. Poisson's ratio, if you care about estimating the mass of your part, mass density is in here. thermal conductivity if you're doing some thermal FEA, thermal simulations. So it's got preloaded a bunch of different material properties, and that makes it really convenient. So I'm just going to select that steel, hit apply. Excuse me. All right, you can actually see the appearance of the part changed a little bit there. All the materials have an associated default quote-unquote appearance, basically the color and texture of the part as it is displayed. But if you want to manually change that, you can actually right-click on the part, navigate. You got some of your basic options here. We're going to go over to Appearances, hit the drop-down menu. We're just going to change the appearance of the part as a whole. If you wanted to do one part with multiple different colors, you could actually just set, like this individual face, you could set to a new color. We're just going to change the color of the part as a whole. And similarly, SOLIDWORKS also has a database of appearances, so you can navigate, you can choose between a bunch of different steel-looking options, aluminum, brass, what have you. As you can see, if you switch between these, changes the color of the part. It'll also change things like reflectivity if you want to do a nice photorealistic render of your part. This is relevant. But let's just say, let's just say I like the look of machine steel, so we're just gonna go with that. And if you wanted to, you can also edit the color over here. If a specific color or appearance you were looking for isn't available here, you can make some tweaks and define it yourself over here. So I'm gonna go ahead and hit OK. And you don't necessarily always want the color to be representative of the final material. Sometimes if you got complicated assembly, even if multiple different parts are going to be manufactured as the same material, you can set them to different colors, and that can be useful for communicating information visually. Anyhow, I think with that is all of the miscellaneous things that I wanted to show with this part. So we are going to call that good. And I think before we move on, I am going to pause here for about a minute. I can see there are a number of you guys hanging out in the Discord. Go ahead and give us a thumbs up if you're keeping up, or if you have any questions, feel free to let Logan or I know there. Okay, I am not seeing any questions, so I'm going to go ahead and move on. Feel free, though, to send a message and to tag Logan, and he can help you out if you guys have any questions. Keep it up. All right, moving on. Like I said, this is sort of a grab bag of different topics. So sort of unrelated topic here is surface modeling. So everything we've talked about so far in these 3 sessions have been in reference to solid modeling, and that is fundamentally what CAD is, at least engineering CAD. But there's a whole sort of additional set of tools that can come in handy from time to time. That is not solid modeling, it's surface modeling. So you're dealing with 3-dimensional, but still 0 thickness sort of bits of geometry. And these are actually accessed, all these tools here that let you create and manipulate surfaces are accessed by a completely different set of tools. You go up to View, Toolbars, and then turn and hit the checkbox on Surface Modeling. For some reason, it's not actually in any of the default ribbons on SOLIDWORKS, but you can only get to it through that toolbar. And that toolbar looks something like this. It's a lot of the same fundamental operations as solid modeling, but you don't necessarily need like a closed contour. So here there's an extrude surface option, a revolve surface option, a sweep surface, and a loft surface. So a lot of the same operations as with solids. And just like solids, the surfaces are controlled by sketches. So you'll still draw out a sketch and then extrude it or revolve it or sweep it or what have you into a surface. And surface modeling lets us, it's almost sort of, a surface is very rarely our actual sort of end goal. It's usually used as an intermediate step in order to do things that are either very difficult with solids or impossible. So sometimes you might use them to trim bodies or to thicken them into a rib or create specific, like if you want to split one solid body into two but without a gap between them, you can do that by creating a surface and then using the split tool and create two bodies from one. So sort of the general workflow might be, so you'll like create a sketch, you'll extrude a surface, create another sketch, extrude some other surfaces, and then in a case like this you might want to like use these yellow surfaces as tools to trim your sort of white surface there. You end up with a surface like this, and then you can thicken that into solid geometry and achieve something like a rib like this, which this exact geometry is actually technically very difficult to achieve with surface modeling or with solid modeling because everything's sort of extruded perpendicular to this surface at every point. Something of a more practical application, or sort of, maybe not more practical, but more commonly used, is for splitting parts. So this here is an example of a customized thruster that we created for the RV team, the underwater vehicle. And this was being 3D printed. And so we had multiple parts that were interacting with each other closely. All the geometry is dependent, but there needs to be some gap in order for it to print properly and for the parts to be able to fit together. Otherwise, if there's zero gap, it'll be way too tight. So I'm actually going to show you real quick. I'm going to pop over to SOLIDWORKS, open up that specific part, and just give you a quick example or a quick demonstration of how this sort of thing generally works in context of a typical part. So I'm going to roll back here to there. So you can see sort of the main duct of this part and sort of this front nacelle were originally all part of the same solid body. And I wanted to split them here. So I drew a sketch here and used the surface fill tool, which is one of these up here. And then I extruded a surface. And then I knit those two surfaces together. So that extruded surface and that original surface knitted those together, so they're now one surface body. And, surface bodies and solid bodies show up separately up here within the feature tree. You can actually apply things like fillets to surfaces. So you can see that just rounded that sharp corner. And then this is the big thing. I then thickened. So that thicken operator there, that actually turns that surface into a solid body. And then you can do something then. And then, for example, you can use the combine tool, which is something we haven't really talked about. It's effectively SOLIDWORKS' Boolean sort of body operation. So if you want to add two bodies or subtract one from another, or take just the intersection of the two, that's what the combine tool is used for. Frustratingly, SOLIDWORKS hides it up in like I believe it's Insert Features. There's a combine tool right here. Anyhow. So effectively what we did there is, because we used a surface and then thickened it, we got an entirely consistent sort of gap between these two parts all the way around. And that is one of the situations where surface modeling can be really handy. Again, the actual geometry, our end geometry is still solid, but using surfaces as an intermediary helped us achieve something that would be tricky to do with just solids. Or maybe not even necessarily tricky, but would just take more effort and more features to achieve. So that is just a quick demonstration of how that sort of thing can be useful. We're not going to go too deep into surface modeling here. This is just be aware that these tools exist and they may come in handy from time to time. As a quick exercise, we're just going to do something really simple, just to get you, very base level acclimated to the tools. We're going to go to SolidWorks. Let's create a new part real quick. And then, so if we wanted to create just a very simple pipe like this, the way to do it with solid modeling would be to create a sketch, draw two circles concentric with each other, one for the outer diameter, one for the inner diameter, and then just extrude. And in a very simple case like this, that is absolutely the most efficient way to do it. But if you wanted to, and there's no real reason to, but just to show you the tools, create a sketch, draw a circle real quick. I'm going to call that 50 millimeters. And then, so I actually have the surface modeling toolbar up, but I'm going to go ahead and close that real quick just so we can show you how to get to it. What you go to is View, Toolbars, and then where is it? It is down here. You have to hit this down arrow. Surfaces, there we are. Click that. It'll turn on the surface toolbar. It might automatically snap over here, but if it does, if you want to, you can drag it out and place it where you like. I like it up here above my ribbon. I actually also have another toolbar that isn't up there by default, selection filters. That's a topic for another day, but oop, misbehaving a little bit. All right, anyhow, so we have a sketch. Now, if we want to, we can extrude that as a surface. So you can see that is completely zero thickness geometry. And then you just like extruding a solid, same tool effectively. You give it you can do blind and give it a specific value, or you can do up to a surface, up to a vertex, midplane, etc. So we now have a surface, and it shows up here under surface bodies. If we want to turn this into solid geometry, I believe this is another situation where the tool is actually not even on the surface modeling toolbar. You can select your surface body and then go up to Insert, and I believe it is under Boss/Base. There is the tool Thicken here. And that is how you turn, that is how you turn a surface into solid geometry. And I believe, that does consume the solid body in the process. Or sorry, it consumes the surface body in the process. And you have a couple different options there. You can do, thicken, 5 millimeters in one direction, thicken in the other direction, or thicken in both directions. And like I said, this is like a very simple tube like this is much more efficiently done just through solids, but just a very brief intro to the tools. All right. Moving on to our, our fourth unrelated topic for the evening. That is skeletonization and other interpart references. So, sort of the way we've been doing, the way we've shown you so far how to do parts, where you create them independent of one another and then you assemble them into an assembly. If you actually want to, make changes in your assembly that affect multiple parts, you have to manually edit those parts independent of one another and create all the changes you want. So if you have two parts that have, a bolt pattern that interact with each other, and you want to, say you have 4 bolts and you want to change it to 6, you have to go into the first part, change 4 to 6, and then go into the second part and change 4 to 6. And in some cases, that's not a particularly big hassle. But if you want to make more substantial changes, or if you have a lot of parts, it can sometimes be a headache. So we might want to find a way to just be able to edit like one thing and have the changes propagate to all the parts that it affect. And one of the ways to do that is with a skeleton part. So a skeleton part is basically, it is a part file, but includes basically just sketches and like datum planes, no actual solid geometry. And you can quote unquote insert that, and we'll show you how to do this here in just a second. You can insert that into multiple different parts, and then have your sketches in this part reference the geometry in the skeleton part and build solid geometry from there. So you can have multiple parts that all have to interact with one another and have their geometry driven by one single skeleton with all the sketch geometry built in. That probably sounds abstract and not particularly clear, but that'll make sense here in just a minute. In fact, I'm going to go ahead and skip this next slide for a minute and pop directly into exercise 3 here. Sorry about all that. Okay, so if I am correct, in the zip file that we provided to you guys via that tiny URL link, if you go to exercise 3, you should see exercise 3 _ skeleton. That should be the part that you have. So I'm going to go ahead, close that, clean up our workspace a little bit here. There we go. All right. So I'm going to go ahead and open exercise 3 skeleton here. All right. So this is a skeleton that we've prepared. Pretty simple one. It just has, your 3 default datum planes and then 1 sketch. So if you edit the sketch, you can see got all of our constraints, got all dimensions, fully constrained and all that. So let's say this is for a underwater, a waterproof enclosure. So this rectangle here corresponds to sort of if we revolve that, that'll create a tube, and then these 2 other closed contours that'll create end caps with O-ring grooves here. But the geometry of all those parts is interrelated. At the very least, the end cap and the tube need to be interrelated, and the tube and this end cap have to be interrelated, because it's a situation where the effectiveness of your part is going to be very sensitive to your manufacturing tolerances and to the clearances in your sort of your nominal geometry. Yeah, I'm actually just going to do this and show you. So what you can do here, so this is just a regular part file, and we can go and create a new part file. And then this is the sort of wacky part. You go up to insert part, and then you can select exercise 3 skeleton there, and just ignore this. So what you've effectively done here, and actually let me back up one sec. When you insert this, there's a bunch of options here for what from this part you actually want to insert. And since this is all sketch and planes, you want to make sure that you have sketches, both absorbed and unabsorbed, and planes turned on. I believe this might actually be turned off by default. So make sure you got those checked. All right. And so this is, it's kind of weird to think about. We've effectively inserted a part into another part, and this shows up effectively just as a feature like any other within our new part here, part 2. And if you hit this drop down, this gives you access to all of the sketches and all of the planes within the skeleton here. So I'm just going to go ahead and hide those. And what I'm going to do here, if you'd like, I believe you can, if we wanted to, we could just revolve directly from this. In fact, I'm going to go ahead and show you that option. Select your sketch, select revolve, select under selected contours, you can actually select which closed contour you want to revolve. So you can select this here, and then axis of revolution is this sort of center line there. And when you do that, you get solid geometry. In some cases, your actual skeleton might not include like fully closed contours and may not be ready to use directly from the skeleton. So I'm just going to go ahead and suppress that real quick and show you the other way to do it. And that is, you can, on this front plane here, I'm going to right click, create a new sketch. And then what I'm going to go to convert entities. And we may have mentioned this in the first session. I don't know why SOLIDWORKS calls it convert entities. It's actually would be more accurately called project, the projection tool. So I'm going to hit that. And this is effectively lets us select any geometry, either from an existing sketch or from an existing solid, and sort of project it into our new sketch here. So I'm going to go ahead and just for ease of selecting everything, I'm going to have make sure select chain is checked. That'll just mean, so if you select one line here, for example, it'll select everything connected to it. So what that effectively does, if we hit checkbox, is we have projected geometry from our skeleton into a fresh sketch in our part. And there are other reasons you'd want to do that beyond just whether the skeleton already had closed contours. We're not going to get into that though. Oh, yeah, it's actually interesting. You end up with a specific constraint symbol here that actually indicates that this is projected geometry. It's a bit hard to make out at this resolution, but actually you could, if you wanted to, you could actually delete one of those constraints and then edit the geometry from there if you wanted to for some reason. I'm going to go ahead and hit Control-Z to undo that. Yeah, so I'm just going to leave that as is. You go back out. So this sketch is independent of the skeleton sketch, so we can actually hide that now. And I could take this and revolve it in the same way. We don't have to specify which contour because there's only one. And then we can just select our axis of revolution. And we get our part. I'm going to go ahead and save that as, I'm going to navigate to my folder. I'm going to save this as exercise 3 end cap A, because there are going to be two end caps that are slightly different in geometry. I'm just going to call this one A. And we're going to save. And for the sake of argument here, I'm going to go ahead and actually set my material to, and you don't have to do this. I'm just going to do it for the sake of completion. I'm going to set this to a pretty common aluminum alloy 6061 T6. Yeah. So now I'm going to go ahead and create another new part. And just like that one, I am going to insert part, select our skeleton again, make sure that sketches and planes are turned on, and again, ignoring the dimensions thing. We have, again, placed our skeleton in a fresh part. And when I am using this technique, if I'm making a bunch of different parts, I'll actually tend to do this once, and then I could save this part as just give part template, and then copy that for all new parts, so I don't have to go through the process of inserting the part every time. But since we're just doing 3 parts, it's not a big deal. And again, I'm going to do the thing where I project the geometry. So I'm going to go to front plane, create a new sketch, go to convert entities, make sure select chain is turned on, and I'm going to select the geometry for the tube. And I'm going to go ahead and revolve that around there. All right, and we now have a tube. And again, for the sake of completion, I'm going to set this material here. I'm going to navigate down to plastics and select ABS PC. It's effectively a polycarbonate, which is it's not exactly plexiglass, because plexiglass actually refers to acrylic, but it's a transparent plastic. I'm going to hit apply, and that actually went ahead, and the default appearance associated with that material is transparent. So that is already hidden. All right, cool. All right, we have our second part done. I'm going to call that exercise 3. I can't type today. Tube. Cool. And now one last time, we're going to create a new part. Go to Insert, Part, Skeleton again, sketches and planes are turned on. Ignore that, and ba-bam. It's going to hide those planes. Again, I'm going to go to front plane, and I'm going to project this geometry. So In this case, just for the sake of the example, these two parts are different. And there are plenty of reasons for, if this is a waterproof enclosure, why you might want those to be different. One of these might have holes for connectors to go through, and this one might be solid, for example. So I'm going to go ahead and do that. And then, again, I'm going to hide the sketch from the skeleton, and I'm going to revolve this here. Cool. And again, I'm going to set that to an aluminum. For commonly used materials, you can actually, this is a sort of a favorites list, and you can manage your favorites to add any material you use frequently. You can add into this sort of shortcut menu there. And when you're doing skeletonization like this, I'm going to go ahead and save this as exercise 3 and cap B. When you're doing skeletonization like this, you're not limited to, it's like you can still add additional features here. In fact, you generally in your skeleton, you only want you want to limit how much information you have stored in here. It's generally best like you only store the information in your skeleton, like the interfaces between the parts. So if I want to add a hole here in this end cap, that's not information that needs to be stored in the skeleton because it just affects this part and not any of the other ones. So I'm going to go to Hole Wizard. Position, select this rear face, place a hole here in the center, go back to type, and I'm just going to make this, I believe, ANSI metric, tap drills. This is somewhat arbitrary. I'm just going to go to M16 by 1.5. That happens to be the actual the thread used on the panel jacks for underwater connectors on the ROV team. But this is just arbitrary just to show you. So, got a hole there. So now, we've created our 3 parts. Now let's assemble them. Going to go to File, New, Assembly. And I'm going to go ahead and insert all of the parts we've made. Cool. And then to constrain these, as we showed you guys in session 2, I'm just going to go ahead and there's actually an interesting case where all 3 of these parts actually have the same coordinate system. So if we constrain all of these to just the front plane to the front plane and top plane to top plane and right plane to right plane. If we do that, just do that for all 3 of these. Because these are all driven from the same skeleton, if we do that, they actually will line up in the same way that they were lined up in the skeleton. Cool. So we now have 3 parts, just like our skeleton showed. We're going to go ahead and hit save this. And I'm just going to call this A.exercise 3. A dot forces this to the top of the list in Windows Explorer. Anyhow. So, why did we bother with that whole skeleton thing? The reason for that is now, let's say we want to change the diameter of this tube. What is it right now? I'm going to go up to, if you guys don't know, you can go up to Evaluate and to the Measure tool. And then for any, you can just select something like that and measure the diameter directly as opposed to going through navigating into sketches or what have you. All right, so this is currently a 3-inch diameter tube. Let's say we talked with the electrical team and they're going to need more room for the electronics that are going to be housed in here. So we want to turn this and we want to bump it up to a 4-inch diameter tube. If we had not skeletonized these, then we'd have to manually go in and edit all 3 of these parts independent of one another and hope we didn't make any mistakes and that everything lined up in the way they were supposed to at the end. Or, because we have skeletonized them, we can just go ahead and open up the skeleton. And by the way, there is no particular need to insert the skeleton as a separate part in the assembly. We can go ahead and open up the skeleton again. Going to edit this sort of main driving sketch, and and we said we wanted a 4-inch diameter tube, so I'm going to change this radius here from 1.5 to 2 inches. And when we do that and save, all of those changes should propagate to all of those parts we just made. So if we go back to the assembly, it'll ask us, models contained within the assembly have changed. Would you like to rebuild the assembly now? Rebuild effectively means refresh, update. So I'm going to hit yes. And ba-bam, all 3 of the parts changed together. And that is effectively the reason for skeletonizing. So, when you're making, particularly in the early stages of design, a lot of dimensions are very fluid, and it can be handy to just only have to go to one place to change all of your major dimensions, and then just have everything update from there. However, that is not to say that there are not downsides to this, because there definitely are. In fact, this is not the only way to quote-unquote skeletonize parts in assemblies. There are a couple other ways, as we actually showed in that demonstration. Let me go back to that. Where was that? There. This thruster part that I was showing you. This is only one part file. This is one.sld.prt. But in effect, they're actually, and these here are actually separate. There are actually eight separate solid bodies in this one part file. There's this sort of front nacelle, there's the main duct, and then there are another 6 bodies that are these are colored inserts. These were printed as separate parts just so they could be printed in a different color and then just glued in. But anyhow, this is effectively 8 separate parts, but we've got them all in one SLD-PRT file, one part file. And this is sort of a way that you can sort of buy, like, in this case, I guess I could have technically made a skeleton part and done everything we just went through in order to do this. You could technically do that, but it would be a real pain in the ass, particularly because this geometry is just much easier to create altogether and then split apart when you've got everything done. So there are advantages and disadvantages to all these different methods. So the insert part method, one of the downsides is it's particularly hard to version the whole assembly. So it's like if I wanted to create an entire new parallel version of that enclosure, that can be hard to do because if you recall when we were doing assemblies, there was an option just to like right click on a part and hit replace component, and you can replace it with a new version of the same part. There isn't an option in SOLIDWORKS to do that with the actual skeleton. So if you want to create a new skeleton for a new version, you have to like go back and manually relink all of the sketch geometry. It can just be a pain. But one of the advantages is that with the insert part method is you can do moving parts. So if you have like a 4-bar linkage, you could have one skeleton part that sort of you have to the skeleton basically has to have all of the geometry as if it were static. But when you make them as independent parts and then assemble them, you can still use all of your constraints such that the parts can move relative to one another. That is a lot harder to do if your parts are just separate bodies within one part file, because you don't have constraints and you don't have degrees of freedom. Everything is sort of just static. So doing separate bodies within one part file is a lot better suited for parts that are in their final implementation static with respect to each other. And personally, I think doing the separate bodies within one part file is particularly best suited for 3D printed parts. I would never really recommend having multiple parts that are either going to be made through different processes, so like a machined part and a 3D printed part, and then also different materials. I wouldn't really recommend having those as the same as multiple bodies within the same part file. Those are probably best done as multiple part files and then assembled. And potentially, if you still want to skeletonize them, you can use the sort of insert part method. Those are just 2 of the ways that I tend to do it. There are a bunch of other different options. Like you can actually just, if you wanted to, you could effectively make your assembly file your quote-unquote skeleton. You can create sketches in assembly files and then just have parts that reference those. But that is another situation where it basically only works there if the parts are static. And there are a couple different options, but this is to give you a general overview. There are multiple ways to do this, and they all come with their own particular unique disadvantages. And it's the frustrating thing is that if you're new to it, those disadvantages don't really become apparent frequently until you're already in deep with whatever you're designing, and it's pretty hard at that point to change. All right, that actually so that covers all of our independent sort of miscellaneous topics here: equations, surface modeling, and skeletonization. So at that point, I think I'm just going to do this one exercise here. This drawing, this is a part that I believe this was exercise 4 from session 1. But before I do that, I'm going to take another sort of 90-second break here. Give you guys an option to ask any questions in the Discord. And I'm actually going to step away here for just a minute. Yeah, so yeah, I'll be right back. All right. I don't know how exactly long that was. I don't know if that was 90 seconds, but I am not seeing any questions in the Discord. So, and it looks like Angela's here too. Yeah, so if you have any questions, you can direct those to either Logan, who's hanging out in the Discord, or Angelo. And if there aren't any right now, I think I'm going to go ahead and proceed. Probably going to end up, we're probably going to finish here decent. Probably going to finish here just in another about 10 minutes, so very much ahead of schedule. Cool. So, this was, like I said, this was exercise 4 from session 1. A simple, sort of mostly revolute part. And I'm just going to give this, I'm going to use this as an example to do a bit more detailed drawing than that first sort of rushed example I showed you guys. So I'm going to find that part. I believe I have it here under exercise 4. Yep, that's where we provided it, exercise 4. I'm going to open that up. Man, SOLIDWORKS is giving me this weird cam messages quite a lot lately. I'm going to go ahead and close out some of the other parts here just to declutter our workspace so we keep less information in RAM. All right, so we got this part. And we want to make a drawing. So new drawing. Actually, you know what? Instead of doing that, I'm going to the ROV team. We actually have a specific drawing template. So I'm gonna exercise 4. Yeah. I believe there probably is like a specific file type for a drawing template, but sort of the simpler, hackier way is just to have a drawing that has the things formatted the way you like, and then copy and paste. Right. So this is actually a specific format that we made that does fit on an 8.5 by 11 sheet of regular printer paper. That is actually one of the other uses for drawings beyond actually making drawings, beyond actually making engineering drawings, is that if you set up a drawing to be 8.5 by 11 and then create a view of a part at 1:1 scale and then print it out, then you can actually have a 1:1 printout of your part. And that's the sort of thing that if you want to do, like, you can use spray adhesive to attach that to like a sheet of plywood or plastic or aluminum sheet stock, and then use that as a reference for like a drill press or bandsaw or what have you. So there are other hackier uses for the drawing part, or rather drawing file type. Anyhow, we can go ahead and insert a model view here. Exercise 4. And then what do we got here? I think just those two views will probably work. And then I could insert an isometric view like that, but I'm going to show you guys, if you didn't insert all the views you wanted when it sort of prompted you for that first, you can go up here to model view, select that same document, and then if you want to select isometric. There is also a way to get other, if you want to like isometric from another direction, there is a way to do that, but we're not going to go into that here. All right, I'm going to change the part scale. So I'm going to go, and I believe these are set up, yeah, by default, they're just using the sheet scale. So I'm going to, again, go back to the sheet format right here, properties, and I'm going to change scale to 2:1. There we go. That's actually that's a little big. I'm gonna go 3:2 and call that good. Cool. All right. So SOLIDWORKS automatically populated this with some center marks, and actually a nice dotted sort of circle here indicating the sort of the diameter of this bolt pattern. That was handy of SOLIDWORKS. So, and I believe I'm going to want one additional view. I'm going to want a cross-section view. So I'm going to go back to drawing, section view. I believe I'm select a horizontal one here. And it will snap to centers. It'll also, this tool should snap to the center point of any line. So I'm going to hit that, checkbox, and then bring down a section view, just because there is there's a whole board through this, so I want to be able to dimension that. And a section view never hurts. So we go over to annotation, smart dimension, and I'm going to start out just by annotating some of these lengths. I actually believe this is a metric part, so before I do that, I'm going to switch units over down here in the bottom right hand corner. I'm going to switch that to millimeters. So dimension, again, I have that mapped to a keyboard shortcut D. If you missed from our last session, the way to do that is you go up to Tools, go to Customize, and Keyboard, then you can search specific. So I think if I search Smart Dimension there, yeah, I got this set up to shortcut D. Again, that's Tools, Customize. Keyboard shortcuts can be really handy for expediting your workflow. Anyhow, dimension. So start out by dimensioning some basic things. I'm actually going to change, I believe that is currently set to display node. SOLIDWORKS does this occasionally where it thinks it's displaying 4 decimal points, but it's not actually. If you need to, you can just change that and then change it back or what have you. And what is... I don't know what the hell it's doing. SOLIDWORKS seems confused. I think I used mostly whole millimeters, so I don't think it'll matter too much, but that is interesting. I don't know what SOLIDWORKS is up to. It's not actually updating how many decimal points it's displaying. We will see if we can figure that out at some point here. In the meantime, I'm just going to proceed. adding a few dimensions. If this is something where CNCing, it doesn't particularly, well, if it's something you're CNCing, then you tend to want, if you have a drawing handy, that'll generally be so you can measure the part after it's made, and verify that the dimensions are what you like. So in that case, you'll tend to want to dimension things that are easy to measure. So like the thickness of this flange is easy to measure with a pair of calipers. So you could do a 5, as opposed to, you could also you could also dimension it like that. And with adding dimensions to drawings, it tends, like with sketches, when you're adding dimensions to fully constrain a sketch, you don't want to over constrain it. So you don't want to provide additional dimensions that aren't necessary. As long as all the information is encapsulated, it doesn't matter. Like, from this that the thickness of this flange has to be 5 millimeters because you have dimension 5 and 10. But in drawings, it doesn't, because these aren't actually doing anything to dimension the part. This is just annotating. It doesn't hurt to have some additional information. It's better to err on the side of having more dimensions than you actually need than having fewer. Because if you, particularly if you create a drawing to go to the ME machine shop and you realize you accidentally missed a few dimensions that are actually important information that you need, that is a bad thing. But having more dimensions than is strictly required to fully define the part is not a particularly big deal. So I'm just going to add a few more dimensions here. This looks to be like a groove for like a retaining ring. That's going to be important to denote both the width and the depth. Interesting. So a fractional, I don't know what is up with SOLIDWORKS where it's not actually displaying the decimals as it should be, but anyhow. Yeah, so with Revolute parts like this, I tend to like to have sort of all of my length-based dimensions in one view and then have a radii in another, radii or diameters, but that's just a matter of personal preference. And it doesn't hurt to note the same thing multiple places. You'll notice that SOLIDWORKS, if you select a like even here, this doesn't look like a circular edge, but of course it is. SOLIDWORKS will automatically add that diameter symbol to you there. I believe I showed you before, you can add things like center marks and center lines that might not automatically populate here. Maybe if I want to add a line that indicates that corresponds to the central axis of that bore, you could do it like that. Again, that's just the center line tool right there. So I believe if you wanted to, you could dimension the actual the radius if you'd like. I believe most lathes tend to operate in just diameter mode, but I believe you can switch back and forth on certain ones. Anyhow. These sorts of labels auto-populate, you can move those, and when you're doing that, it's moving it relative to this view, so that will still move when you move that. Just going to add a few more dimensions. I might be missing a few things, but for the sake of brevity, I'm going to mostly leave it there. The only other things I'm going to add are angles here. It's a bit tricky. You can see in the isometric view there is a tapped hole right there, and that, at least presumably based on the CAD, that has to be indexed relative to this bolt pattern. It may not be, and that's the sort of note you can add. You could add a note here that says, you'll dimension this hole, but you could add a note that says, does not need to be indexed accurately. With respect to bolt pattern. That's the sort of thing that is handy to include a note for. And part of the reason for that header is not showing up properly. I don't know what the hell saw it. Oh, there we go. Man, SOLIDWORKS is a bit buggy today for some reason. But yeah, that's the sort of thing that notes are handy for. Part of the purpose of GD&T in general is to, like I said, we're not going to get into the specifics of how to do that, but one of the goals of GD&T is to reduce the number of notes that are actually necessary on a drawing. Particularly handy if the people manufacturing a part don't speak the same language. Cool, but okay, yeah. So the other thing you might, but let's say it does need to be indexed accurately. Then it'll be important to note the angle here. Just like the Smart Dimension in Sketches, the Smart Dimension tool in drawings will automatically infer what you intend to actually dimension here. So it'll let you do, it knows you want an angle between those two holes, or those two lines you selected. Another important thing we haven't talked about yet is the hole callout tool. You select that is useful, and select a hole. And I believe it does talk to, let me go back to the actual part here. I believe that the hole callout tool in the drawing draws information from the hole wizard that you can use when actually making your part. That's one of the reasons to use the hole wizard, is for documentation purposes. And you'll notice there, so it automatically, it knows that the hole is a through hole, so it goes completely through the flange in this case, so it'll automatically add through all. And it knows there are 4 of them, hence the 4x. And then again, that is just the diameter symbol. There may be a way to get SOLIDWORKS to automatically include this information. I have not looked deeply into it, but I would like to note here that this is an M3 clearance hole. And just like dimensions in Sketches, dimensions here in drawings, you can also add things to the dimension text right here. And you can also add additional symbols if you'd like, I believe. Yeah, things like that. Yeah. Yeah. And then, so this is also another standard hole here. I'll go ahead and delete that note, clear up a little space, since pretenses, we don't need that. So I'm going to go back to hole callout, select that there, and cool. So that did pull information from the hole wizard. It specifically knows that is an M5 by 0.8 millimeter. 6H there is actually a tolerance class. That's not particularly important, but it automatically knows that this hole is supposed to be tapped to a specific thread, and it went ahead and gave us that thread type. Cool. And I believe that is most of the information, most of the basic things I wanted to cover here. Again, this was a template that we actually used on the ROV team. Again, to edit information here in the title block, even as you double click, it doesn't do anything. In order to edit the title block, you have to go back up to here, sheet format, right click, and hit edit sheet format. And that'll let you edit the border. Like, I think you could delete the border if you wanted to. Maybe it doesn't let you. None of the selected entities could be deleted. I think you'd have to delete it through there. Anyhow, we'll keep the border. So yeah, you can go in here. I believe this is exercise 3. Whatever the name of the part is, any information you need to fill in. I could add here that this is me. Add a date, or the date. And these are some common notes here you'll find on drawings. If you don't specify tolerances on every individual dimension, you can add sort of your base tolerances here, and then also note things like deburr and break sharp edges. Very basic information that you want to communicate. Oh, and then material. Again, I believe there is a way to get this to link to the material that you specify in the actual model, but I do not currently know how to do that in SOLIDWORKS. I know how to do that in NX, but I could specify here that 6061 T6 aluminum, and maybe your particular alloy doesn't matter, in which case you could just specify just aluminum. Cool. I believe that is basically everything I wanted to specify. Ooh, the scale does auto-populate that by default. That is important information to note, or that is important information to make sure is clearly communicated. And you may sometimes actually change For like isometric views, you may occasionally change that to a different scale, just to make it all fit nicely on your paper. In this case, we wouldn't have to. But if you do something like that, I generally recommend adding a note that the scale of that individual view is different. Yeah. All right, I believe that is all the information I wanted to show you guys. There is another exercise. We're not going to do it, but there is another part here if you want to get some more practice creating drawings. And definitely feel free to reach out to any of us here in the Discord if you guys ever want if you guys have additional questions in the next couple days, or if you'd like some additional sort of resources for learning or additional exercises to play around with. Feel free to let us know. I think with that, I am going to call it good. Angelo, Logan, and I here will stick around in the Discord for another, 10 minutes or so. If you guys have any questions, feel free to let us know. And I think with that, I'm going to go ahead and end the stream. Thanks for hanging out with us this evening. I hope you guys learned some stuff.